Welcome to the lecture on vibration measuring instruments. So far we have studied the forced vibrations and free vibration. We see that any structure that is subjected to some force, it responds to that force. The response can be in terms of displacement, velocity, acceleration. Okay. Also, there is some frequency content in that response. So, in case of free vibration, usually the structure vibrates with its natural frequency, or if it is damped structure with some damped natural frequency, that is called omega d, that is equal to omega n root 1 minus zeta square, where zeta is the damping factor. When there is a forced vibration, so the structures has two responses. I mean, the total response is sum of two responses, that is the transient response and the steady state response. So the transient response die out due to damping, effect of damping in the initial initial some time. However, the steady state response that remains till the force is applied. So if there is some harmonic force, as we discussed several cases in which the structure or the system is subjected to harmonic force like F0 sin omega t. So usually the response of the structure comes to like x equal to x sin omega t minus phi, where so the response contains the some amplitude of the sine curve, and there is some phase lag with respect to the force. Moreover, when we differentiate the x equal to, so if we differentiate x equal to x sin omega t minus phi, so we can get x dot, okay, that is omega x and cos omega t minus phi, or x double dot, that is minus omega square x sin omega t minus phi. So all these three terms, they are displacement, velocity and acceleration. So they are the response properties of some structure. Moreover, there is omega, frequency and the phase. So now the question is how we will measure these vibration responses when our structure is vibrating, and we want to know with the measurement with some experimental system that what is the vibration response, what is the displacement response, what is the velocity response, what is the acceleration response, then what is the frequency content. So all these parameters, if we want to know, we have to measure, and so we have to use some instruments. And because we have already dealt with some vibration, the fundamentals of vibration and theory of vibration, we know that if we are going to measure the vibration using those instruments must be designed based on the theory of the vibration. Then only they can measure the vibrations. So here basically the theory that we have already studied, that we will use to discuss the design of the vibration measuring instruments. So in this first lecture of this vibration measurement, we will discuss today these transducers and vibration pickups, the basics of this measurement. So let us see here. So what could be a basic scheme of the vibration measurement? Okay. So here we start with some structure or machine that is vibrating. So we have some structure that is vibrating. Okay. So there is some physical structure that exists and that is vibrating. It has some oscillatory motions and we have to measure. So we have to use some instrument. So we call it transducer, vibration transducer or vibration pickup. Okay. So they are the instruments. So what is a transducer? Transducer converts a signal into electrical signal. So it converts a physical quantity into an equivalent electrical signal. So like more specifically, it converts the change in that physical quantity. So it if there is some change and it converts into equivalent change in the electrical quantity. So if there is some displacement, velocity or acceleration or force, so there is some change. So corresponding we will it will show the change in the electrical signals, and so there is some relation between this physical quantity and the electrical quantity, and with that relation we can know that from the electrical measurement of that electrical signal we can know what is the change in that physical parameter or physical quantity. Okay. So here we have a vibration transducer and they gives us some signal, electrical signal. Okay. So when we get the electrical signal we have to apply some amplifier or signal conversion instrument. So why do we need the signal conversion instrument? Because the electrical signal, the change in the electrical signal is very small, and so it is not very strong to with respect to the noise or some other vibrations. So basically noise. That's why we have to amplify this signal using this amplifier. So we use this signal conversion instrument, and that amplifies that signal. Now that signal we have, now we have to see on the display or on the computer screen. Okay. So we can for example, if we have some signal, we are measuring some vibration, and so we have this signal that we are measuring. So suppose we are measuring x and versus time. So this is a signal that we will obtain. Okay. And here time is 0. So here we have for different. So here there is some delta t, the time step. Okay. So at each time step we will get the value of that quantity, the physical quantity, that is displacement here x, and we can see this signal on the screen. Now when we have signal, we have what we will do with this signal, because this signal is not giving us enough information. For example, this signal is very simple, but it could be also some signal like this. So from this kind of signal, I mean how we will understand that what does it mean. So we need to do some data analysis. We have to do the analysis of this signal, and from the analysis of this signal, so there are several analysis, like we can do the fast Fourier transform. Okay. So we can know the frequency content and amplitude of that frequencies, that corresponding to those frequencies we can know the amplitude of that signal. Okay. So this data analysis will give us the characteristics of the vibration behavior. or vibration response, and that is what we want from the measurement. So, from this process of this measurement, we can know the using the instrument, we can know the finally the vibration characteristic or vibration response of a physical body. So, first let us discuss some general types of transducers. So, transducers, as I said, that they transform the physical variable into some equivalent electrical signal. So, it means there should be some relation that the electrical signal is related to some mechanical or mechanical aspects. For example, there is variable resistance transducers. So, variable resistance transducers means that those transducers utilizes the characteristic of resistance change, and they link it with the vibration measurement. For example, you know that the resistance of a wire depends on the length. So, resistance is proportional to the length of the wire. So, if the length is increased, resistance will increase, and if the length is decreased, resistance will decrease. So, this relation can be used as a resistance transducers. Similarly, there are some piezoelectric materials, and piezoelectric materials, when some force is applied, they develop some charge on their surface. So, and that charge can be converted into the voltage, and that voltage can be measured. So, this characteristic of the material, so force, application of force is some physical or mechanical quantity of the some vibration characteristic, okay, and we are converting into the corresponding electrical voltage. Okay. Then electrodynamic transducers, these transducers, they use the characteristic of this inductor, that is because the voltage in an inductor is proportional to the rate of change of the current. Okay. And so, they use the principle of electromagnetism, and they can with some rate of change we can relate to the velocity, because velocity is also the rate of change of displacement, and we can relate it to find the change in the voltage of that inductor. Then there is linear variable differential transformer transducer. So, this is also based on the principle of the coil and the inductor voltage, and so we will discuss in further details these aspects. So, here we have the variable resistance transducers. So, we can see that the strain is change in length. So, if I have some wire and its initial length is L and it is extended as delta L. So, the strain is delta L by L, and we know that the resistance is proportional to the length of the wire. So, strain is proportional to delta R by R. Then this proportionality needs some constant term that will depend on the wire and its relation with the strain and resistance. So, here we say epsilon, we say K. So, here K is known as the gauge factor. So, this is known as gauge factor, and so there are the transducers known as strain gauges that uses this characteristic, and the gauge factor is the constant for that strain gauge or for that wire, and we can use the strain gauges to measure and the strains in some mechanical systems. So, these transducers are based on the resistance. Now, these strain gauge can be, if we can see the figure, when there is some strain gauge attached to some cantilever beam and there is some mass, and so this mass is vibrating and we want to capture the vibration of this mass, and we have attached this strain gauge here on this cantilever beam. Now, this the strain at that location of the strain gauge will be depending on the displacement x, because if it is more displaced from its equilibrium position, the more strain will be there. And so, by measuring the strain and by relating the strain to that x, we can measure x. Now, here there are some circuits, because there are electrical strain gauges, and so they follow some circuits, and this particular circuit we call Wheatstone bridge. So, here is this Wheatstone bridge. So, here is input voltage and here is output voltage. So, this is called Wheatstone bridge, and we can see the relation that E equal to R1 R3 minus R2 R4 by R1 plus R2 and R3 plus R4. So, when this bridge is first balanced, and when it is balanced there is no any current, and so the output E is 0. When we use this bridge, so let us say R1, this strain gauge we apply to measure on some vibration measurement, we attach some on some cantilever, and so we say this is Rg, because R gauge. So, this is the main the strain gauge that is attached to the structure, others are not attached. So, when this is attached and our bridge is this balance, there is no any voltage E. So, E is 0. However, when there will be some change, some vibration, there will be change in the resistance of the strain gauge R1 or Rg, and so the Wheatstone bridge will be unbalanced. And so, there will be some current and then some voltage E. So, E will be non-zero, and we can measure E, and we can, by measurement of E, we can convert it to measure the strain E, and the strain is can be related to X. So here we can see this final formula epsilon equal to, so we can measure epsilon equal to K delta E by K V R 0. So here we know we know the, because gauge factor, because gauge factor is given for some the strain gauge. R0 is some constant that depends on the resistances R1, R2, R3 and R4, and delta E is the change in the output voltage that we measure. We know this, and so we can know the strain, and this strain we can relate with X, and so we can measure X. Now there are another type of transducer known as piezoelectric transducers. As so, when there are certain materials in on this earth, when they are subjected to some pressure, there is some charge developed on the surface of these materials, and they are known as piezoelectric materials. So here we can see there is some plate of piezoelectric material with thickness T, and there is some force applied on the surface in the X direction. So it is perpendicular to the surface, and and if we connect the two surfaces, we can know the what is the voltage developed on the surface due to the application of that force, and by measurement of that voltage, we can know that what is the force or displacement force applied on the surface. So here Q is the charge on the surface, that is equal to K into F. K is some constant of the piezoelectric material and F is the force, and force is area into pressure. So we can write KAPX, and this E is equal to VTPX, this formula. So voltage sensitivity. So the general piezoelectric materials, they are quartz, rochelle or lithium sulfate. However, when we unload the material, so again the material is in its initial state, and so it is discharged. So based on the piezoelectric materials, there are some transducers, some vibration pickups they are made. So one example is the accelerometer. So piezoelectric accelerometers, they are very frequently used. They are frequently used in the measurement of the vibration responses. And so here you can see there is some spring and mass system, and there are some disc of piezoelectric materials, and they are between the mass and the base. And so when there is some vibrations of the mass, they measure the difference between the mass and the base, because base is attached to the surface which is vibrating. So here are some electrodynamic transducers. So we know that when some electrical conductor moves in some magnetic field, there is some voltage generated in the conductor, and so this principle is used here to design or to make this kind of transducers. And the voltage that is developed is dLV, where D is the magnetic field density, magnetic flux density, L is the length of the conductor, and V is the relative velocity. So here this transducer is working based on the relative velocity. So V this kind of transducer can be used for velocity pickups. Moreover, this magnetic field can be produced by two way, either we provide some permanent magnet or we use the electromagnet, means we provide we have coils and we pass some current, and so there will be some magnetic flux created in that coil. There is another type of transducer that is called LVDT. So, linear voltage linear variable differential transformer transducers. So, in this kind of transducers, as you can see, there are this is the primary coil and there are two secondary coils. So, this primary coil is is given some input voltage, AC voltage EI, and there is some magnetic core, some material, magnetic material core, and here are the this output is taken from the difference between the two secondary coils. This magnetic core is such that if it is in the middle of the two secondary coils, there is the cancellation of the voltage, because equal voltage and opposite voltage in both the secondary coils. So, they cancel and so they produce the zero voltage. However, when there is the movement of the core, because the core is connected to the displacement measuring some instrument. So, if it is displaced, so it moves. So, it is out from one end of the secondary coil and it is more inserted into the other end of the secondary coil. So, this system also so there is some magnetic coupling, and from this system measures the voltage away from 0 when there is some displacement of the magnetic core. However, there is also the directional measurement, because the coil, the magnetic core can be moved to one direction. So, it enters in one coil more. If it is in opposite direction, it enters more into the another coil. So, it also measures the direction and so measures the vibration in the with respect to the equilibrium point. So, here this is the linear voltage displacement response of this system for a small movement of the this core. So, we can see here 0 and it is more linear in the both side, in the positive and negative displacement side. Now, vibration pickups. So, vibration pickups are used so they are used in conjunction with transducers, and they are also called seismic instruments. They contain usually mass, spring and damper system. So, when this is the mass, spring and damper system, and this system is attached to the vibrating body, and here we can put some transducer like piezoelectric transducer, and so we can know the relative displacement between the base and this mass, and that relative can be measured from this transducer, and we can with the help of the theory of vibration, we can relate this relative displacement to the base displacement, and we can measure this the vibration of the structure. So, this vibration pickups can be of different types. It could be so their name differs based on what they are going to measure. If they measure the displacement, they are called vibrometer or a seismometer. If they measure velocity, they are called velometer or velocity pickups. However, if they are used to measure the acceleration responses, they are known as accelerometers. So I stop here, and thank you for this lecture, and see you in the next lecture.